This section we're going to be dealing with series that have some of the terms have negative signs. And let's start with the first series that I want you to take a look at. It goes like this: 1 minus 1/2 plus 1/4 minus 1/8 plus 1/16 minus, and you'll notice that every other term is negative, and we could write this series in the following format. I can go k equals 0 to infinity, and I can do -1 to the k, because when k equals 0, -1 to the 0 is 1. That gives me the sign at least here. This is just going to make the sign happen for each of the terms. When k is 1, I'll get a negative. When k is 2, I'll get a positive. And well, you get to see, for the odd values of k, I'll get negatives, and for the even values, I'll get positives. Now, how do I control these things? Well, I got 1/2, then 1/4, then 1/8. To me, this looks like a series with a geometric series with common ratio of 1/2. So let me try this and see if it's what I want. So I'm going to put 1/2 to the k, and let's check it. I've already checked the positive and negative part, so I don't need to redo that again. Let's check and see what else happens here. When k equals 0, I get 1/2 to the 0, so I get a 1. When k equals 1, I get 1/2. K equals 2, I get 1/4, and everything works out. Well, we already know how to work this particular series. All the geometric series have the same formula. As long as they start at 0, I'm going to combine and write this as -1/2 to the k power, since the -1 and the 1/2 are both raised to the k. And then I can use the formula, since k is starting at 0, I can use the formula for geometric series, and I'll get 1/1 minus that common ratio. And that looks like I'm going to get 1/3/2. So the series adds up to 2/3. So the first foray into this business wasn't so bad. We can't really deal with a series unless we have some sort of a pattern to the negatives. If the series were all negative, it's no big deal. We just apply all the stuff we did for positive series, except we have negative signs. On the other hand, if the negatives are not in any kind of an order, if it's just a hodgepodge, then we don't really have simple formulas or one single way to handle those. Those require individual efforts. Let me move on to the next series. And we know this series as the harmonic series. And it looks like this. This one starts at 1 and goes to infinity, but it's simply 1/k. We know that this series diverges. We know from the P-series test that this series diverges. However, look at its alternating version. I'll even write this out because I think it's so important. So we have the alternating version. It looks something like this: k equals 1 to infinity. If I try to do -1 to the k times 1/k, what's going to happen is when I have k equals 1, I'm going to get -1. And this series, just for some convenience, I prefer it to start with a positive term. So I'm going to write it as -1 to the k plus 1/k. That way we get 1 minus 1/2 plus 1/3 minus 1/4, and this goes on forever. And then I let my calculator give me a few values for it. Let me see, when n and Sn. And remember, Sn is always the nth partial sum. So it goes from k equals 1 to n, negative 1 to the k plus 1 times 1 over k. So I threw some values in. When I threw in k equals 10, these are all approximate. I got approximately 0.65, then 0.69 when I put in 100 for n. I put in 1,000 and I got 0.6926, and then 5,000 I had 0.6930. That's to 4 places. That actually rounds to a 0 in that spot. My calculator gave up after that. Let's take a look at some formulas for S1 is no problem, that's 1. S3 equals, I just want decimals, so I'm going to use my calculator and throw these in. I already have it in the calculator. I've already been playing around with it, but I'm going to choose small values to show you what's going on. I have it set to give me the decimal version. So for S3, I get 0.83 with a bar over it. And then S5, let's see what I get for that. .783 with a bar over it. And now what I want you to notice is that these odd, if I look only at the odd terms, do you notice the numbers are going down? Let me go and shoot some more at higher values. So let me try 105. I get 0.698. These are approximate now. Was it 0.698? Let me grab 107, the odd one right after that. That's going to be important with what I talk about. I get 0.698 also, but it has a 77. This had a 78, and this has a 77. So I'll put 0.698 S107. 3 decimal places, you're not getting to see all the action here. So I'll do 109 and see if I can start spotting where it goes down. So put a 9 here. 0.6977 again. And then I'll try 111. 0.6976. Well, I'm tired of playing these little games. Let's go 1113 and see if I can change the decimals. Ah, thank you. 0.694. .694, and that was 11113. Then I'll jump down some more. I don't know, 4,099. I only want the odd ones. When you get really high, the calculator gets sort of mopey about it. 4099. And I get 0.693. Now, it may not be going fast, but it is decreasing. So these are all the odd numbers. So the odd terms, let's say S sub 2n minus 1. If I start that at 1 and go off to infinity, let's make sure I get the right numbers. When n is 1, we'll have S1. When n is 2, we'll have S4. We'll have S3. Then when n is 3, we'll have S5. So this is modeling. This gives us all the odd terms. So this sequence is decreasing. But you can see I'm starting to lock in some digits here. 69, 69, 69. my calculator can't do a lot higher than this, but 693 was locked in actually. And it's bounded below. It is bounded below by 0.69 probably. But I could actually just say it's bounded below by 0. It doesn't matter. All I need is to show that it's decreasing. It doesn't have to be decreasing from the beginning. It just at some point on it has to be decreasing. And it's bounded below by a certain number. That implies, this means that the limit as n goes to infinity of the s2n minus 1s exists. So the odd sums exist. The limit, that is. Now let's go to the even. So I'll start at s sub 2. And I'll go back to my calculator. .5, easy enough. S sub 4. .583 with a bar over it. Let's see, S6. .616 with a bar over it. And I'll do as before. Let's get some big values. Let's do S of 100. I get 0.688. S102. I get 0.688 again. This had a 0.68817. This has a 0.688269. This number is a little bit bigger. I'll have to jump down quite a bit to get more decimals than just 0.6. So let's try S1002. What is that approximately? .6926. Let's do a bigger number. Jump down some more. Let's try 4002. Give it a second. 0.693. Let me have the next decimal after that. 30. Well, you can see here this sequence is an increasing sequence. So the sequence of even partial sums, it's increasing, and bounded above. Really doesn't matter what. I can see that these are increasing and increasing and increasing. My guess is it never gets out of 0.69, so I would say bounded above by, just to be on the safe side, I'll say 0.7. It doesn't matter. As long as it's bounded above and it's increasing, it's guaranteed to have a limit. So the limit, as n goes to infinity, of s sub 2n exists. Well, what we have now is but look at what's happening here. The even terms are going to 0.693, but they're going up to it. They're going up to it. And then the odd terms are going to 6.693, but they're going down to it. So that's interesting. But it certainly looks like they're going to the same limit, don't they? Now we do have this. Let's take a look at an S2n minus 1 is the odd terms up to 2n minus 1. So I'll have a And let me go 2n plus 1. a1 minus a, actually, I'm thinking ahead before I do this right. This is 1 minus 1/2 plus 1/3 minus, and this, I don't know how far I'll need to go, but let's just say I get to 1 over 2n minus 1 minus 1 over 2n plus 1 over 2n plus 1. And then look at s sub 2n. That equals 1 minus 1/2 plus 1/3. And this will go on, just like before, 1 over 2n minus 1 minus 1 over 2n. Now look at these things. They're virtually identical to each other. The only difference is this particular ending here. Now I know that the limit, as n goes to infinity, s sub 2n plus 1 exists as above. I didn't have to say, I could have put a plus here and everything would have been virtually the same. But then we have this extra term out here. Well, this is easy now. This piece goes to 0. So what we have then is the limit, as n goes to infinity, s sub 2n plus 1 equals the limit, as n goes to infinity, s sub 2n. But the sequence itself of partial sums, s sub n equals 1 to infinity, is nothing but the union of these two sequences, s sub 2n minus 1, n equals 1 to infinity, union, we've seen that before, that's where you put set elements together, s sub 2n, n equals 1 to infinity. Then for large n, here we'll have n bigger than some mysterious capital N. We would then have that Sn is either going to be an odd or an even index. Well, if this thing is going to some limit, and this thing is going to the same limit, what does that say about this thing? Well, if this is going to a certain limit, that means that our values are getting close to the limit value. The odd numbers are getting close to the limit value. But here the even values are also getting close to the limit value. So if we let the limit as n goes to infinity, s sub 2n plus 1 equal, I don't know, let's call it L, which equals the limit as n goes to infinity of s sub 2n. Then this piece right here, if I have a large n, then I am guaranteed, since it's either even or odd, that this Sn minus L will be less than some mysterious epsilon, because this or this are both getting close to L. Well, this is going to imply that the Sn, that this limit also exists. What that L is, what that number L is, we will have to determine in the future. I can give you a hint. It's the natural log of 2. I guess that's not really a hint, it's actually telling you what it is. But the reason I went through all this rigmarole, I didn't prove things, but I did close to proving things. The purpose of doing all that was to describe an alternating series test. And I'll tell you exactly what we had, what we did in it to show that we are going to have a convergent sum. So you're going to have something like this. K is going to equal 1 to infinity. It should start at 1, but I'll put negative 1 to the k plus 1, and then I'll say a sub k. So that's going to equal a1 minus a2 plus a3 minus a4, etc. The a's, incidentally, I'm considering them to be positive, so minus this is definitely, this piece right here will definitely be a negative number, this piece right here will be negative, etc. as you go down the line. Okay, this thing converges if you have two things. S sub n equals 1 to infinity, eventually decreases. And limit, as k goes to infinity, the individual terms of the series go to 0. I'll show you where that was important for us. We put something under this to indicate how important it is. Alternating series, every other term is negative. Remember, we do not have methods where the negatives are interspersed throughout differently than every other term. So let's take a look. Where do we have? I'll look right here. If you'll notice, it was crucial that this term went to 0 in order for us to guarantee that the limit of the even and odds was the same thing. Now, the decreasing part, if you look at the fact that the S2n was increasing, and the odd s's were decreasing, and the even s's were increasing. Oh, I've misstated my proof, or my theorem here. Right here it needs to be fixed. I need convergence if the AK eventually decreases and the limit as k goes to infinity, AK goes to 0. With the AK eventually decreasing, that means that the even terms will eventually start to go up and increase. And the odd terms will start to decrease. Whenever this eventually means that it can happen anywhere in the sequence. Maybe it could happen at k equal a trillion, or k equal Google, or some monstrously large value. But this eventually means that at some point the terms will start to go down, and they will stay going down for the rest of the time. So from whatever point on, say, let's just give an example, say a sub capital N. From that point on, like a capital N plus 1, a capital N plus 2, a capital N plus 3, those terms all the way off to infinity are decreasing. If that happens, and we have the limit as AK goes to 0, then we have convergence. Now, I urge you to look through the proof. Fat chance, right? But I urge you to look through the proof, because you'll see that the steps that they take are practically identical to the ones that I used to show that this particular series decreases. And they do go through the steps. There's an outline version of it in the book. There's also a full version of it in the index, I believe. But let's focus on some examples and how to use them. So, we'll start with example 1. And my series is k equals 1 to infinity, negative 1 to the k plus 1 over the square root of k. Now, I got to prove those two things. First, I need to know that the sequence of these k terms is eventually decreasing. So let's look at the terms. A sub k equals 1 over the square root of k. A sub k plus 1 equals 1 over the square root of k plus 1. Well, we know this much. I know that k is less than k plus 1. K is, after all, a positive number. So 1 over k has to be greater than 1 over k plus 1. Now, this is an important step. Since the square root function is an increasing function, it preserves the order like this. That means if I have one number bigger than another number, when I take the square root of both sides, I will maintain this inequality. It won't switch on me. So I can take the square root of both sides, And, well, those are the terms of the series then, because the square root of 1 is just 1. So what I have then is a sub k is greater than a sub k plus 1. Since I didn't specify a k, this series decreases for the whole thing. Or the terms of the sequence decrease. So a sub k equals 1 to infinity is decreasing. Secondly, are the terms going to 0? So the limit as k goes to infinity, a sub k is the limit as k goes to infinity, 1 over k to the 1/2. I like that better when I'm working with it. The square root is not very fun to work with. Remember, as long as this number is positive and the exponent is positive, this piece here is going to infinity. So this does equal 0. So, because we have a decreasing sequence and the limit goes to 0, we know the series converges. Alright, now my a sub k's are the sine of 1 over k. So let's see if these are going to decrease or not. First, let me get the limit as k goes to infinity. Get that moved out of the way. Sine of 1 over k. Since the sine function is continuous, you can rewrite this with the limit brought inside. Well, that limit is easy. Everybody knows that's 0, so I have the sine of 0, and we know that equals 0. So I have that part. The limit of the terms is going to 0. Now, is it decreasing? It may be kind of hard to see when you're dealing with numbers like 1 and then 1/2, because we don't take the sign of numbers like that typically. They're not ones that we would know in our head. So what we might do is this. Consider f of x equals sine of 1 over x. It's similar in nature to this, but the reason for going to an x is to allow my variable to be continuous. That way I can take a derivative. When you take the derivative first of the sine, and you'll get cosine. Then you get 1 over x. And then the derivative of 1 over x is negative 1 over x squared. What kind of a number is this going to be? Well, x starts at 1, so I have cosine 1, and then x gets bigger and bigger and bigger if it's to follow k values. So like x equals 2, cosine of 1/2, cosine of 1/3, blah, blah, blah. The fact is, from 0 to 1 happens to be in the first quadrant. In fact, the angle here, that's pi over 2, which is 1.57 something. So the angle that only goes up to 1 in radian measure is all in the first quadrant. So cosine is positive for that quadrant. This is guaranteed to be a negative number because x will never be 0. This is negative. This is less than 0. What do you know about a function whose derivative is less than 0? F of x must be decreasing. If f of x is decreasing, and that means for all x's it's going down, so if you have f of x versus f of x plus 1, it's going down. This means that f of x has to be less than f of x plus 1. Well, if I replace my x's with k's, f of k must be less than f of k plus 1. But that's just sine of 1 over k must be less than sine of 1 over k plus 1. So, and this makes sense. as these values inside of here get smaller, the sign values, I was copying that. Decreasing means that. The next one must be less. Less. Well, at least I caught myself. Unfortunately, I'm not sure where I'm going to edit it out at. So this is going down, and you ought to know that. As the angle comes down in the first quadrant, the sign values get smaller and smaller until they converge to 0. So what do we got? We have a decreasing sequence. So we have the AK are not only decreasing, but they're decreasing to 0. So the series converges. Now this brings us to the next notion. That's called absolute convergence. And it just says this: a series is absolutely convergent if the sum k equals 1 to infinity of AK converges. So I should have probably said here a series. The series is going to look like k equals 1 to infinity. I should probably, let me do this. Let me put my absolute values around here, because then I'll allow this to be positive or negative. So I just say a series of terms. It's convergent if you replace each term with its absolute value, if that converges. So as you saw, we know that this series, k equals 1 to infinity, diverges. But k equals 1 to infinity, negative 1 to the k plus 1 times 1 over k converges. So the alternating version of the series converges, while the original series does not converge. If a sub k, k equals 1 to infinity, converges, but the absolute value terms does not converge, then we say that the sum k equals 1 to infinity a sub k is conditionally convergent. So in our example here, this one right here, the harmonic series, we would call conditionally convergent. So the first theorem goes like this: THEOREM if the absolute value of AK converges, then so does the original series. So absolute convergence, the phrase is this: absolute convergence implies convergence. Obviously, the other way around does not work, because the harmonic series is one of those series that does not converge absolutely, but it does converge conditionally. Let me see how I'd want to write this. Let's assume that A sub k is a convergent series. So I'm going to rewrite it as this. I'm going to rewrite it as, actually, let me do this. Let me start off with the original series. Okay, that's going to equal A sub k plus the absolute value of A sub k minus the absolute value of A sub k. Like that. Now, you can imagine I'm only going up to a certain n at this point, but I'm going to break it up in the following format. Now, this piece right here has two options. This is going to be either 0 or twice the absolute value of AK. It really doesn't matter. Zeros or this thing. Whatever I have there, no matter what happens, this is going to be less than or equal to summation to absolute value of K minus summation absolute value of K. Because when I put 2 that, this is accounting for the times it might be 0, or it could be twice that. So if I just put twice that for the whole thing, it's definitely going to be less than or equal. But both of these converge. I can take that 2 out front like this. This is still the same thing. I have a convergent series and I have a convergent series. So it doesn't really matter. I can now plug them together and get this. Which, I mean, I could have gotten this without all this business. You should know by the triangle inequality I could have done this. But nonetheless, since this converges, that forces this to converge. I should have told you, since the first term was a positive number, the next term was negative. How do I want to put this? Remember, the terms are supposed to be eventually decreasing at some point. Or actually, what happens? The terms have to go down to 0 at some point. So this action could all be happening where k is bigger than some mysterious n, and then I have all these inequalities working for us. All right. We already know that this series converges. But the absolute value of it here, if I take the absolute value of each of the terms, we simply get a p-series, 1 over k to the 1/2. We know that this diverges because that exponent is less than 1. Alright, so since it converges because the exponent is less than 1, this series is conditionally convergent. See, example 4. Here we have summation k equals 1 to infinity, negative 1 to the k, plus 1. I'd like to start in a positive term. Tan inverse. I think I did the same mistake here too, didn't I? And we have tan inverse. Well, what's this going to do? Well, take a look at tan inverse first of all. First, determine if the series is going to even converge at all. Take a look at the tan inverse k term. Limit k goes to infinity. Tan inverse of k equals, well, as k goes to infinity, tan inverse goes to pi over 2. So what that means is that these terms are getting close to plus or minus pi over 2 because they're alternating terms. Well, that's not equal to 0. So we don't even have that this thing is going to 0, so the series diverges. And we can move on to the next problem. Well, this one's not going to be too hard. We know if we look at the function f of x equals e to the negative x, everybody by now probably knows what that thing looks like. It crosses when x is equal to 0, at y equal to 1, and it nosedives down to 0 quickly. So that the fact that this is going to 0 is going to force this to go to 0. So that's not a problem. Okay, does it decrease? Well, you can look at the graph and see that it certainly does decrease. How would you know it decreased, though? You can do this, f of x equals, without appealing to the graph, how would you know that it actually decreases? There are several ways. One way is to do this. Look at the differential version of the problem. F prime of x will equal e to the negative x, but you got to take the derivative of what's up top. E to the x is never negative. So that forces this to strictly be negative and function decreases. That means that this also decreases. That was one way. A second way is to look at it this way. If I compare e to the negative, if I look at the k plus 1th term versus the kth term, what I can do then is break this exponent up. So I'll have negative k minus 1 equal, I'm not going to put equals, that was a mistake. Put an inequality when I get to it. Okay, and then this can be the left side can be written e to the negative k times e to the negative 1. But then I can rewrite this as e to the negative k divided by e. Well, e is bigger than 1, so there's no question that this is less than e to the negative k. So go ahead and put our less thans in front of all these. And this guarantees that the sequence of e to the k's is decreasing. So whatever you need, we have the limit is 0 and it's decreasing. So this series converges. But I'm going to go even further. Does it absolutely converge? Let's take a look at that. How about absolute convergence? Let's take a look at that. So when I look at k equals 1 to infinity, the absolute value of negative 1 to the k plus 1 times e to the negative k, that just equals k equals 1 to infinity e to the negative k. Is that going to converge? Yes, it will. Watch what this equals. Some k equals 1 to infinity, 1 over e raised to the k power. Well, now this is a geometric series. And this is less than 1. So in fact, you can actually write out what it equals. It equals 1 over 1 minus 1 over e minus 1, because since this series starts at 1, I got to subtract off the 0th term. Whatever, it doesn't matter, it converges. So the series converges absolutely. Had we decided to do that at the very beginning, none of this other stuff would have been necessary, because we would have known that the series converges. Once you have absolute convergence, the series itself converges. Well, now, this is a little bit different. I am going to shoot for absolute convergence first and see what happens. K equals 2 to infinity, absolute value of negative 1 to the k all over ln k. That's going to equal summation k equals 2 to infinity. this k up here should be a k plus 1. I always want to start, well, if I wanted to start this as a positive number, I'll put a k up there. Alright, so I'm going to get 1 over ln of k, and what's going to happen? Well, we know as k goes to infinity, ln of k goes to infinity also. So the terms go to 0. That's not a problem. Limit k goes to infinity, ln of k equals infinity. So lim k goes to infinity, 1 over ln k equals 0. But while it does that, that's really not, and that will help me with this type of convergence here. I mean, with conditional convergence, if I have to go that route. But what can we say about this? Is such a series like this going to converge? And if so, what will it converge to? Well, this one is tough. While the terms are all positive, how do they compare to something? Well, let's see if you know this. ln of k is less than or equal to simply k. K starts at 2 now, so let's see if that's true. I think perhaps a picture may be the best way to do it. Ln of x crosses at 1 and goes like this. So this would be the y-axis, and it tends to it. So that's y equals ln of x. And then we have this thing here, which would be y equals x. So x is definitely greater than ln of x, no matter what, as long as these guys are positive. So k is bigger than ln of k because these are positive. But remember, when you take 1 over that, you've got to switch the inequality, like so. Well, wait a minute now. That then implies that 1 over ln of k is greater than or equal to, I can actually have greater, but it doesn't really matter, 1 over k, and we already know that equals infinity. So the series does not converge absolutely. So no absolute convergence. However, I did see that the terms are going to 0. Are they decreasing? Is 1 over ln of k a decreasing sequence? But once again, I don't really know, like, since the natural logarithm is an increasing sequence, if I have a k and then I have a k plus 1, you'll notice that the order is preserved. Look at the y values here. There's no question, with a lower x value comes a lower y value. See, you can see here, here's the y value associated with k. And then if we go to the next one, the y value associated with k plus 1. So this would be ln k, and then this up here would be ln of k plus 1. So I think because ln is an increasing function, it preserves the order. So since we have k is less than k plus 1, then ln of k is less than ln of k plus 1. Well, then I can flip it when I do 1 over, and the sequence is decreasing. So it's going to 0 and decreasing, but the no absolute convergence, so we can describe this as having conditional convergence. All right, to test for absolute convergence. So I'm going to first test for absolute convergence. So I am looking at the absolute values and the absolute values for an alternating series do nothing but wipe out the -1 piece. And k is going from 1 to infinity. Now, what I'm going to use, it's particularly nice when you see things like this with exponents. You would think of the root test, maybe because this is to the k power, but the ratio test works very well too, because you'll be comparing e to the k versus e to the k plus 1, and you can factor out an e. And the ratio test was built for things that have a factorial in it. In fact, I might suggest to you, if you see anything with a factorial in it, I would probably do the ratio test as my first test no matter what. So that's what I'm going to do. I'm going to do the ratio test and see what happens. That means I'm going to look at e to the k plus 1 divided by k plus 2 factorial all over e to the k divided by k plus 1 factorial. And remember, I want to look at the limit as k goes to infinity of this. For some reason, when I do the ratio test and write that, I never remember to put that initially, but it doesn't matter. I do put it eventually, so we have the limit as k goes to infinity. Now I'm going to rearrange this. I'm going to have e to the k plus 1 over e to the k times k plus 2 factorial all over k plus 1 factorial. So I can do a lot of canceling. For example, I can take out this e to the k, and then I'm left with just an e there. And then k plus 1 factorial, oops, I got these upside down. You can cancel here. I can take out the k plus 1 and leave k plus 1 factorial and just leave k plus 2. Well, this is not a big problem at all. I'm going to have, I'll factor out the e, and at the limit as k goes to infinity, 1 over k plus 2, that will equal e times a 0, which will equal 0, and that's one of the things that we know makes the series converge. So it is absolutely convergent.